Can Mike and Pat get more power from a supercharged 6.2 LSA? The quest begins, plus more distributor tech, today on Engine Power.
Today on Engine Power, we're digging into a production power plant from General Motors that earned its fame as the most powerful engine in Cadillac's 113-year history. Now, it was so popular in the CTS-V platform, it later found its way between the subframe rails of the 2012 ZL1 Camaro. Now, in Cadillac trim, it produced 556 horsepower, and in Chevy trim, 580. It is the 6.2-liter Supercharged LSA. The block is a unique aluminum casting that has proven itself in strength and durability. Now, it has a 4065 bore and a 3.622-inch stroke, making it 376 cubic inches. 6-bolt cross-bolted main caps are a big player in its strength. The cylinder heads are Rotocast 356 T6 aluminum with 260cc intake ports and 80cc exhaust ports. Valves are 2165 and 1590 respectively. Combustion chambers are 69.8 cc's for a compression ratio of 9.1 to 1. The Supercharger is a 6th generation 1.9 liter with 4-lobe high twist rotors. It has a broad range to produce excellent low-end torque and not skimp on high-end horsepower.
As this build progresses, you'll see the trick internal engineering that GM had to do to get the numbers and reliability from this power plant. And with a few affordable mods, these engines will make north of 700 horsepower and maintain that legendary reliability. And for us, we'll be making some extensive changes, like adding over 50 cubic inches, upgrading the valve train, and getting some custom CNC port work done from the best source in the automotive industry. We're talking about the School of Automotive Machinists, one of the top high-performance engine building schools in the country. They cater to everything engine building and have programs for cylinder head porting, block machining, and learning how to program and operate state-of-the-art CNC equipment. To prove they are at the top, they campaign a full race program where students build and maintain some of the fastest all-motor cars in the country. Like the owner's NMCA Real Street Camaro that has enough trophies from wins to fill a boxcar. And his wife's Texas Mile Monster, where she went over 200 miles per hour and has plenty left to set a record at the next meet. Not to mention their in-house Copo Camaro program. We upgraded one to meet current rules. The other was a top qualifier at the recent NHRA Fall Nationals.
So what's our journal size?
They're just a tick under the low.
Chris Bennett is a SAM engine block instructor and tuner for the race program. He's been here quite a few times. Kyle Kinsman is a recent graduate who was selected to give us a hand for his hard work and dedication through the block machining and cylinder head programs.
Wow.
Chris, we sent you guys the stock LSA heads and the Supercharger. Tell me what you did with them down at the school.
First thing we did was we gave the heads to the CNC department. Okay, the students and instructors ran them through the CNC program. We've done a lot of R&D on the LS series of heads. The LSA is very similar to the LS3. So we went through the heads, then we gave the blower to the cylinder head department, where that was hand ported to match the CNC intake runners, and then we ported the inlet and the other passages in the blower.
Very nice. Now, with the other parts on this table, what's your prediction on power?
Easily 750, maybe 800.
And that's what about overstock?
200 overstock.
Let's see it. Let's get started.
Let's do it.
And that all starts right here. This LSA short block is the foundation for our build. Now, we're just not going to zing this thing apart and throw all the pieces in a crate. We're going to carefully disassemble it to show you the features and engineering of this exceptional factory engine, and that all starts after the break.
We're back and putting Chris and Kyle from SAM to work. Now, the externals will come off first, starting with the balancer. It turns 3 belts. The rear 4-rib turns the AC compressor, the center 6-rib turns the power steering, alternator, and water pump, and the front 8-rib turns the supercharger. The oil pan is a 6-quart unit that is cast with bosses for a liquid-to-air oil cooler. Total capacity for the engine is 8 quarts. The timing cover is next. It houses the camshaft sensor. Kyle, what were some of the key selling points that made you attend the School of Automotive Machinists?
Actually, it was by asking racers who they respected most in the industry, and after hearing what they had to say, I decided to look and see what programs they offered, and decided it was a really good fit for me. Things I learned from block to the proper parts to use, the proper camshaft and selection, all the way to the heads and the right valve springs. I mean, there's a lot to it, and they teach you everything you need to know.
Behind that cover is the crank-driven oil pump. It's more powerful than naturally aspirated LS3 and L99 engines. And a unique spring-style tensioner keeps the chain taut. Using a flat screwdriver, apply tension and lock it in place with a pin for removal. A single row timing set makes the link from the crank to the camshaft. Now the cam retaining plate is removed and the cam is spun a couple rotations. That pushes the lifters into the lifter retainers. This allows cam swaps with the heads still installed. By removing the fastener, the tray and 4 lifters can be removed ×4. The camshaft is next to come out. It's a hydraulic roller with very mild specs. Remember, it has to meet emissions.
With the engine rolled over, Chris will remove the windage tray, which keeps oil from interrupting the flow into the oil pump. Another unique feature to this engine are piston squirters. Their job is to keep the bottom of the piston cool, since extra heat is generated from additional cylinder pressure from the supercharger. The rods are powdered metal and use a cracked cap. That means the rod is made as one piece and the big end is literally broken in a controlled manner, making the two pieces unique to each other. No mixing up caps here. The main caps are typical of an LS engine. They use 2 side bolts and have a 4-bolt main. This crankshaft is unique to the LSA. It's a drop forged steel piece that will handle in excess of 1,000 horsepower.
The LSA crank uses an 8-bolt flange for additional clamping strength and also has a 58-tooth reluctor wheel, compared to a naturally aspirated 6.2-liter that uses a 6-bolt crank. The 8-bolt crankshaft isn't applicable to us since we're running a Trick aftermarket flex plate and 6-speed automatic transmission.
With the disassembly part crossing the finish line, it's time to start our build. Now, this block will need a slight amount of clearancing to drop in our stroker assembly. Because we're increasing the cubes from 376 to 427, our crank is going from a stroke of 3622 to 4125, and that means we need to make a little bit more room for the rod bolt to clear the bottom of the cylinder. We'll drop the new Lunati crank in on the old bearings, then we'll mock up a rod and piston assembly and install it in its bore without rings. We'll snug it up and then rotate the crank down and mark where the bolt contacts the block. We'll repeat this on each cylinder. Then I'll take a die grinder and remove just enough material to let the bolt pass through the bottom of the cylinder with about 60 thousandths clearance. With our grinding complete, we'll lay the crank back in and verify our clearance. If everything checks out, the block will go in the washer for a final cleaning.
The new crankshaft came with a 58-tooth reluctor wheel, and it needs to be installed. For that, we'll use this Goodson fixture and a little bit of heat. The ring can be pressed on or heated like this. Do it in a rotating manner so it's heated even and expands enough, probably good, so you have time to align and locate it. It only goes on one way. We'll be back after the break.
We're back and continuing on this LSA build. It's time to check the bearing clearances. New coated Clevite bearings are placed in the main saddles and the caps. Then the caps are torqued to factory specs. The first pass on the inners, 15 pound-feet in sequence. Then follow up with the outers in the same manner. Now the inners are turned 80 degrees for their final torque, and the outers are turned to 53 degrees. Finally, the side bolts are snugged down to 20 pound-feet. With the new crankshaft on our Goodson crank stand, the OD of the main journal is measured with a mic and recorded as well. Using a dial bore gauge, which any engine builder should have, the ID of the bearing is measured and recorded. Repeat this for the other 4 journals. Those 2 numbers are subtracted from each journal, and that is the clearance. This Lunati crankshaft is from their Signature Series line. As we mentioned earlier, it has a 4 1/8 stroke. To reduce inertia weight, 7/8 inch lightning holes are drilled in the rod journals. The journals are ground to 125 thousandths radius and are micro-polished. This crank will support well over 1,500 horsepower. With it in its new home, the main caps are torqued down to the same specs we used during clearance checking. Finishing it up, the crank's end plate comes in at an excellent 5 thousandths. Next up, Chris and Kyle will check rod bearing clearance. Just like the mains, the crank's rod journals have to be measured, and that measurement transferred to the dial bore gauge. New Clevite H-series bearings are slid into the Lunati forged H-beam rods. They have a 6/125 center-to-center length and a bronze bush small end. Finishing them out is an ARP 2000 rod bolt. To achieve proper clamping force, the bolt has to be stretched a precise amount. An ARP rod bolt stretch gauge will tell us exactly how much the fastener is stretched when it's torqued. As per Lunati specs, the bolt stretch should be between 5 and 5.5 thousandths, which should happen between 65 and 75 pound-feet. And we're in the green zone. Just like the mains, the clearance is checked, then recorded on the build sheet.
DSS Racing supplied the custom pistons for this build. Now up top they have a negative 29cc dish and LS3 style valve reliefs. They accept a 1.5, 1.53 millimeter ring pack and have an inch 052 compression height. Now these were ordered with their patented X groove. Here's a look at how it works. On the upstroke, fuel wash and normal debris are swept into the X groove and forced down into the oil pan. Now that keeps the protective oil film intact on the critical areas between the skirt and the cylinder wall. On the downstroke, excess oil and debris are swept into the X groove and exit the oil drain back holes, keeping the clearance between the piston and cylinder wall cleaner, which reduces the oil load on the oil ring. Total Seal supplied the ring pack. It sports a 3 millimeter chrome-faced oil ring. The second is cast Napier, and their C33 coating is on the stainless steel top ring. Total Seal assembly lube will coat the rings and skirts for installation. With clean and lube cylinders, the piston and rod assemblies are going in. Using a piston knocker, carefully drive the piston through the compressor, making sure a ring does not catch the deck. Also be careful down low that the rod does not nick the rod journal. Once seated, install the cap and snug it down for now. This procedure is repeated the exact same for the other 7. Referencing our build sheet, to get the required rod bolt stretch, we're torquing them to 75 pound-feet. We have a rotational torque of 14 to 15 pound-feet. By comparison, a 350 small block Chevy is 35 to 40.
That ain't bad.
No, that's a good oil ring for the combo too. Should be good.
Brian Tooley Racing sent us this billet camshaft that's been custom ground to one of his signature profiles. Duration at 50 is 231 degrees on the intake and 248 degrees on the exhaust. The lobe separation angle complements our supercharged application and drivability at 120. Lift at the valve with a 1.7 rocker is 617 and 595. Now a bronze thrust plate from Comp Cams is installed, along with the factory chain guide and tensioner. A Comp Cam single row hex adjust timing set is next. And finally, we can degree the camshaft. The lifters also came from Brian Tooley Racing. They are hydraulic rollers that will drop in with the retainer trays.
All right, guys, we met the goal, getting the short block together. Thanks again for all the help. Greatly appreciate it.
No problem.
John, pleasure to see you.
Sir.
Have a good race.
Thank you.
Take care,
See ya.
guys.
Locking out a distributor for tuning and performance control. That's next.
We're back and almost done for today. Now our new oil pump has been hand ported on the inlet and the outlet by Hubbard Racing. That allows for a better oil flow rate to better protect the engine. The pressure spring is shimmed for higher idle pressure, and you can order yours from Brian Tooley Racing. With alignment shims installed, tighten and torque it in place. With the pickup and windage tray installed, the factory LSA pan is proven, and that's why we're reusing it. A straight edge is important to use at the rear to align it with the block. Now tighten it down. This engine is in full short block status, and I must say it's a pretty bulletproof combination. Now there's still plenty of trick parts to get it to the stage of dyno ready.
That includes these trick cylinder heads that flow some pretty outstanding numbers, along with parts from Nick Williams, Metco, and Weapon X. We'll also be building the rest of our heat exchanger system so the intercooler stays nice and cool and you don't want to miss it. Tools are how we get work done, and quality tools like Matco are in a league of their own. This is their 1/4-inch drive ADV socket set, which includes millimeter sizes from 4 to 15 and standard sizes from 3/16 to 9/16. They feature the OptiTorque system, which applies torque to the fastener sides, reducing corner round-off. High visibility markings will keep you from reaching for your glasses as well, and they're available in 1/4, 3/8, and 1/2-inch drive sets, located in Matco Distributor, or check their website for prices.
Here's a new product from Design Engineering Inc., or DEI. This is their new Onyx Series flexible heat shield that is made out of a combination of advanced textiles to produce one of the best heat shields on the market. Now, it's made from heat-treated glass fiber and molten aluminum that are formed into a tight weave. Now, these things can withstand temperatures up to 1,350 degrees. They come with all stainless steel hardware, and you can pick yours up at most of your retailers for about 48 bucks.
Holley and Weiand are bringing electronic fuel injection to the big block Chevy crowd with this new Track Warrior Series manifold. It uses a permanent mold casting to keep the runner walls a consistent thickness for about a 10 to 20% weight savings over a sand cast one. It's designed using computational fluid dynamics software for superior fuel distribution and more power. It's for oval or square port cylinder heads and comes with either a Dominator flange or a 4150 series, plus it even comes with fuel rails. Get yours for around 315 bucks from Summit Racing.
Ignition timing is obviously a crucial part of engine tuning, and having total control of the timing helps maximize an engine's output. Now, the distributor is what dictates when the energy fires the spark plug, so today we're going to show you how to lock one out. Most distributors you deal with have a timing curve in them. That means when the engine is idling, the timing is set at its minimum position. As the RPMs are increased, weights and springs in the distributor move the position of the rotor to advance timing, sometimes as much as 24 degrees.
Let's say, for example, you have an engine that checks at 10 degrees of ignition timing at idle, say 800 RPM, and then you increase the RPM watching your timing mark until the advance levels off, say 5,000 RPM in our case, and it now checks at 34 degrees. That means you have 24 degrees of centrifugal or mechanical advance in your distributor. Different distributors will vary from that up or down, but it's important to check yours to see how much yours has in it. The vacuum advance on a distributor is there for the sole purpose of emissions and drivability, pulling additional ignition timing in at light load and partial throttle situations like normal everyday driving. That's why it's important to have it hooked up to a manifold vacuum source instead of a constant vacuum source. We like to have total control over the timing in the engines we build. Most are high-performance bullets that are built for a specific purpose. MSD distributors have a provision in them to lock the distributor out if you want, and most racers will want to control their ignition curve electronically with a box like an MSD Digital 7. They don't want to rely on springs or weights to set their timing curve. The first thing we need to do is remove the rotor. This gives us access to the springs and weights. As RPM increases, the weights are forced away from the center, which moves the rotor, advancing its position. This is what we'll remove to lock out the centrifugal advance. The springs need to be removed, which is easy. Just pry them off the post. Now the weights can be removed, and the roll pin securing the bushing can be tapped out and removed, along with the bushing. Back on top, I'll separate the rotor shaft from the main shaft and remove the nut and washer along with the advance bushing. Rotate the rotor shaft 180 degrees and align it with the hole on the opposite side. Secure it down. Replace the bushing and tap the roll pin back into place. With all of our unused parts left on the table, the rotor can go back on. Now there's nothing left in the distributor that will cause a timing variance at any RPM, and that's how you lock out a distributor.
Well, that's it for Stage 1. Make sure you check out Stage 2, which is coming up soon. We'll see you next time.